Right, continuing on directly from where I was before, this is section 3.3, Math 204. When is a function differentiable? Complex. When is a complex function differentiable? And you've seen some results already about this. And you know how I've been promising some really good stuff? Yeah, well, this is the good stuff. Right. We're getting towards it. Okay. Definition. A function from the complex numbers to the complex numbers is one analytic at z0 if it is differentiable at every point in a neighborhood of 0. Z0. 2. Analytic on an open set if it is analytic at every point in the set. It is entire if it is analytic at every point. Let's see. Okay, now some people will say holomorphic as well, aka holomorphic. And some people say complex analytic, to distinguish from real analytic. Analytic, as you will soon see, analytic is really saying that the function can be expressed as a power series, that its derivatives exist at any order. These functions, analytic functions, are the creme de la creme of functions. They are beautiful. They are wonderful. They are things to be, as you shall soon see, desired. Anyway, examples. dz 1 over z equals negative 1 over z minus 2. Yep, plus 2, you should prove it. This exists if z is not equal to 0. So f of z equal to z inverse is analytic on the complex numbers minus 0. Not entire. dz of the modulus squared exists at 0, but not elsewhere. Prove it. So, f of z equal to the modulus squared is not analytic anywhere. Analytic functions are important. This is a great concept. If a function is analytic at a point, then its derivative is also analytic at that point. Thus, if a function is analytic, on an open set, then its derivative is analytic on that open set. This is a really important thing. And to the derivative of an entire function is entire. Okay, the proof relies on integration. Oddly, excuse me for the sniff. Oddly relies on integration. Right, which comes back to a very, very important theorem formula called the Cauchy integral formula, which very roughly says that f of z is equal to 1 over 2 pi I times the integral of f of s over s minus z ds. And the Cauchy integral formula also can be used to show that I'm running out of ink. Let's see if we can get this through. F dash of z. No. Hold on. Okay, I'm back. I have ink. The derivative of z of f at z is equal to 1 over 2 pi I integral f of s over s minus z squared ds. So the point here is that the value of an analytic function is determined by an integral of the values of that function in some neighborhood. I'm not telling you what I'm integrating over here. Well, okay, no, I will. I'm going to put a C down here. What I mean by that is we've got some point Z, and I've got a line, a circle, for example, in the plane, a line in the plane, and I'm integrating over that line. So this says that somehow the value of an analytic function at z is an average of the values around the circle where you divide out by some amount. And the same goes for the derivative. So because when you differentiate, it's really an integral, assuming that this term makes sense and can be integrated against, then you get the derivative. And that's what makes this work. But in order to prove this, you have to have this stuff first. We haven't proven the Cauchy integral formula yet. So you're going to have to wait for a proof. But hopefully that that helps to demonstrate why I'm excited about this. There's cool stuff in the background here. There's real, very interesting mathematics coming up. Okay, theorem. Cauchy-Riemann equations. So important, I'm writing it out nicely. Suppose f from complex numbers to the complex numbers is given by f of x plus iy is equal to u of xy plus I v xy, where u and v are functions from the real plane to the real numbers in some neighborhood of x0 inside the complex numbers. So I don't need this to apply everywhere, just in some neighborhood. Then if f is differentiable at z in this neighborhood, then two thens, del u del x is equal to del v del y, and del u del y is equal to minus del v del x at y in the plane. So these things here, these two equations, those are the Cauchy-Riemann equations. Okay. Moreover, if u and v have continuous first order partial differential derivatives, differentials that satisfy the Cauchy-Riemann equations. Yep. Two n's. Two n's is deliberate, not a mistake. In a neighborhood of z, then f is analytic at z. This is a cool theorem, but you're going to get some even nicer goodies to chew on coming up. Okay, proof, not terribly complicated, just working through the details. F dash z, the limit fz plus h minus f of z over h. This is equal to the limit, well, h goes to 0, u. Now I'm going to write u and v as having dependence on z just for the moment, because I don't want to split up quite yet. Well, okay, no, I'll do it. So this is u x plus the real part of h, y plus the imaginary part of h, plus I v, x plus the real part of h, y plus the imaginary part of h, minus u x y minus I v x y, all divided by h. I can split this up into the complex component and the real component. So this is u x plus the real part of h, y plus the real part of h, minus u x y over h, plus the limit v x plus the real part of h, y plus the real part of h, minus v x y over h. And now we do the same kind of idea that we've done many times before. If h is real, then the limits are equal to, I don't want to give you bad habits, are equal to, well, if h is real, then this is just y. So this is an equation for a partial derivative, and that would be del y, del u, over del x. That's that. And there's an I there, plus I times this thing, which is v del x. And if h is pure imaginary, well, again, this is just an x, but that would have an h in it. So this is the partial derivatives with respect to y. So it's del y, del u, del y. But, so that's real, but this would be complex because it would be pure imaginary. There would be an I in front. 1 over I is minus I. I over I is just 1, so this is v. So, as, these things have to be equal, because they're all equal to the derivative, which has to exist somewhere. Excuse me for sniffs, that's not very good, is it? I have sinusitis, that's an excuse, just a problem I have to deal with, and the sniffing is related to that. Yeah, okay, so equate real and imaginary parts, so this implies that del u del x is equal to del v del y, and del v del x is equal to minus del u del y, which are the Cauchy-Riemann equations. Wonderful. Okay, the other direction I'll skip the proof of. You can find it in books on complex variables. It relies on some real analysis, Taylor's theorem, with a remainder, and basically putting this back together to show that the limits all appropriately exist. It's not hugely. Mathematicians sometimes say that a theorem is very informative when that theorem provides information that tells you something about how ideas are related or how objects behave or anything like that. Anyway, so this is not particularly informative. Okay, so in particular we know that f dash of z, we've got some formulas for it now. Del y del x plus I del v del x. Woohoo! We knew that. Yep, and we have minus I del u del y plus del v del y. Yep, that's great. We know what the modulus of this thing is. This is going to be, there's a whole pile of expressions. From here it's going to be del u del x squared plus del v del x squared. It's also going to be del u del y squared plus del v del y squared. Yeah, it looks good, right? You can mix and match the terms. As long as you change the functions up top. And in particular, we also know that the determinant of a matrix called over the page the Jacobian. Determinant of the matrix del u del x del u del y del v del x del v del y. Right, things that might not come up again for a little while, but things that are nevertheless important. Okay, we're getting close to some real meat. Examples. Fz equal to f bar x minus iy. So u of xy is equal to x, v of xy is equal to minus y. So del u del x equals 1, del u del y equals 0, del v del x equals 0, and del v del y equals minus 1. We need, for f dash of z to exist, del u del x to be equal to del v del y, but this is the same as saying that 1 equals minus 1. Oops. And this implies that f dash of z does not exist. So it's not analytic. Easy. Here's another example that does it the other way around. No complex differentiations. This is x plus I y. So u x y equals x, v x y equals y, del u del x equals 0, del u del y equals 0, sorry, that's 1, del v del x equals 0, del v del y equals 1, need del u del x equal to del v del y, and that's okay because that's 1 equals 1, tick, and we also need del u del y to equal minus del v del x, and that's okay because this is 0 equal to minus 0, tick, which implies that f dash of z exists. One more example. Okay. So for the derivative to exist, we need del u del x to be equal to del v del y, which implies 2x equals 2y, which implies x equals y. Oops. I haven't written that down correctly, have I? What's the Cauchy-Riemann equations? No, there's right. In a neighborhood. And now any neighborhood of z, x plus iy, is going to be such that the x and the y's are independent of each other. That's just a line. Which is an issue. Maybe. Yep. And that's that for section 3.3.